precisely, it's pretty easy to establish that it's constant, okay? That it's not varying, and so varying with time. And so just knowing that alone, even if you just called the value of the acceleration of gravity something like g, which we could leave the exact value to be determined later. That's all it takes to use calculus and come up with the kinematic equations, right? Because if we keep in mind that we know the relationship between acceleration and velocity and position, right? We just know that velocity is the derivative, velocity is the derivative of position with respect to time. Acceleration is the derivative of velocity with respect to time, right? So times are independent variable. Then we can easily solve these differential equations and get answers, to get these equations that make sense. So let's take this one. Let's just kind of rehearse what we did. If dv over dt, right, dv dt equals a, then that's starting to look like something that we can deal with now, just now, right? That's a differential equation. All a differential equation is, remember, is just an equation with derivatives in it. And so to solve this thing, we're starting to get a technique for that. First step is we're going to break it up into differential form, right? So we'll just multiply both sides through by the variable of differentiation, dt. dv equals a dt. And then we do our anti-differentiation process. We just take the antiderivative of both sides to undo the derivative, right? And so that unlocks the v, which is what we're trying to get. We're trying to get a formula for v. So these guys cancel, and we get velocity, right? On the other side, we get this strange animal that we now know how to deal with, right? And we could even replace that a if we want to. We could even replace that with a g if we want to be specific. But we just used a, just the case of just constant acceleration, which is more useful because that applies to any situation with constant acceleration. But we could call it g if we want to also. And then all our answers, and we just end up with answers in terms of little g, acceleration of gravity. So either way, when that a or g, it's a constant, right? So we can pull that out front, and we just have the antiderivative of 1 dt, which is just t, right? And so we get our at or gt plus some constant. There's our general solution, right? If we want to get a specific solution, then we got to be able to plug in a point, which it doesn't seem at first like we have, but we actually kind of do. Not really a true point, but at least we can find a name for this constant that makes sense. Because if we think about substituting a value of 0 for t, that's a meaningful, even if it's not pinned down precisely, it could vary from situation to situation. It's a meaningful constant. The initial velocity is something that we'll want to know, or presumably could even measure, right? And so if we plug 0 in, we get the velocity at time 0 is just, this term goes away and we just get c1. And so we establish that's the meaning of this constant. It's just the initial velocity. And so there's our first formula. First kinematics equation. The velocity as a function of time for any constant acceleration is just acceleration times time plus whatever the initial velocity was. Right? Okay, that's good. And then we can just do that again. We know that v equals dx dt, and so we can set up another differential equation that we can solve, right? Which we did. Can't remember how far we got if we finished, and I guess we kind of just about got to the end. Same thing, we'll just multiply both sides by dt to put it in differential form. Notice when I multiply this side by dt, I'm multiplying the whole thing, right? So I need it in parentheses. And then I'll just anti-differentiate again to get rid of the d and give us x as a function of time. Time is our variable over here, right? And then we'll just anti-differentiate term by term. And remember, we established kind of by association with what we did in differentiation, that must be okay. What we said was, remember, that when we were focusing on derivatives, we could always just differentiate like a polynomial, or if we had a string of terms, even if it's not a polynomial, if I have a sum or difference of terms, I can just differentiate term by term. And each one of those separate terms in the derivative gave us its own term in the answer, right? Because we had that one-to-one correspondence, we could just reverse that process, and there's still, those arrows go both ways. And so that means that if we undo that derivative, it should be associated with those terms in the antiderivative. So that's good. That means we can also, when we're doing an integral like this, or antiderivative I should call it for now, we can still just treat it term by term, which makes it convenient. So the antiderivative of some constant a times t, we could break this part up into a times the antiderivative of t dt, right? That's just t to the 1. Now, what did our power rule tell us that's going to be then? This part right here just gives us, what do we do? We haven't had a lot of practice with this, but do you remember what our rule was for anti-differentiating a power? We take that exponent and we go plus 1, good. We add 1 to it, and then we divide by, by that also, right? And then we'll add a constant, which we'll just lump together at the end in one big constant. And then we have our a out front, right? So there's this term, okay? And then this other term right here, this one's a real simple one. With this one right here, this is just going to become v naught times the antiderivative of 1 dt. So that's just going to give us our v naught t, right? And then both of those contribute to our overall constant down here. They both kick in a little piece. So that's our general solution. Can we do a little better than that? Well, yeah, we can do the same trick as before. We can say, what about at t equals 0? Beginning, initial time. We start the stopwatch. Then we get our initial position, x of 0, equals 1/2 a times 0 squared, which is 0, plus v naught times 0, which is also 0, plus c2. So what's the meaning of that constant then? Initial position, sure. All right. So we know then that c2 equals what we might call x naught, initial position. Right? And we end up then with the equation x of t equals 1/2 at squared plus v naught t plus x naught. And these are vectors, and we will get into the vector aspect of this for now. That's more, we can do that in physics, but there's the equation, right? And I think the way you guys wrote this, you said, all right, well, let's define delta x as being final position minus, I'll leave the vector stuff off here. I said I would, and I didn't. Final position minus initial position. So I'll just subtract this from both sides and end up with displacement equals 1/2 at squared plus v naught t. And I think that's probably that's the way you guys wrote it. Okay. There it is. We just derived that equation, right? And the only thing we started with was that we're dealing with constant acceleration. So that gives you just a little bit of an inkling, maybe, why calculus is it. I mean, if you want to, that's anything you do in math and science of any significance, anything is based on calculus. Okay. All right. So, new topic. Let's look at, and this is, let me preface this by saying this is kind of our job now. What we did the whole first part of the year, or most of it, we just started to open up some new doors here, but mostly what we did is we dealt with differential calculus, and all that really amounted to was the first fundamental problem in calculus of finding tangents to curves. That was really it, right? If we had some function f of x, and we want to know, we talked about this, but let's just real quick remind ourselves what we were doing. If we want to find the instantaneous rate of change of this function at some value, we could call it c if we want to. Until we had differential calculus, there was no way to do that. The best we could do is find slopes of secant lines, which are average rates of change over some interval, right? And we could make that interval small if we want to, but we'd always end up with an approximation. You know, we could say, okay, what if we made that interval something like, you know, 0.1? Well, then we get, our answer is this, which has got to be pretty close to the answer. But we can never be exact until we develop calculus. And all we really did with the calculus, remember, and this is really a cool process if you kind of reflect on this now, having know how to do it. We just took the limit as that delta x went to 0. And because we kind of knew the mathematics of limits, we were able to turn those into essentially some formulas, which is the differentiation rules. And so now we're able to do this very quickly with just our calculus tricks or shortcuts. But that's what we've worked on. So that's one very important problem that calculus solves that we've pretty much handled. Okay, the next one, which is arguably even more important, it might sound a little weirder, is this. If I've got some function f, I want to be able to add up an area under that curve, say between a and b. So literally what that means is I want to do, well, this would be kind of cool. Try something here. So I'm going to add up this area right there. Let me see if I can do this. Oh, look at that. Oh, I forgot that. Okay, so we want to be able to add up what that area is, right? Imagine that. Okay, and you might be wondering, why is that such a big deal? Well, it turns out it's a huge deal in calculus. It's a huge deal. Adding up areas under curves allows us to do stuff in physics that is very important. For example, let's say that this isn't just some random mathematical curve. Let's say that this is a force. We're measuring force on this axis and displacement on this axis. I don't know where you are in physics, but can you tell me what the product of force times displacement is? Work. Yeah. Now, work is a big deal in many ways. But in physics, work is a huge deal because when you do work on a system, what are you really doing? Can you tell me? Well, you're influencing, you're adding energy. Yeah, you're adding energy to the system. For example, if I were to, it's not breakable. If I were to pick this object up and set it on a shelf, you know, I've done work on it, right? Because I've had to apply a force in which direction? Upwards against the force of gravity, right? What's the force equal to when I pick this thing up through this distance? Say it again. Say I move it at constant, we'll make this simple. Say I move it at constant velocity the whole time. So it's not accelerating. Okay, what do we call the force of gravity on an object? Weight, yeah. It's weight. I'm supporting the weight, and if I'm moving it at constant velocity, so I'm not accelerating it, wouldn't you agree then, physics types, that the net force on this thing is 0? Right? That makes sense? Okay, so I'm just applying that countervailing force against gravity, and I'm applying this weight upward force through a distance of, say, a meter. Put it on the shelf. What have I accomplished by doing that? Not much, maybe, but what if an ant crawls across the desk and say there's a brick instead of an eraser, and I just give it a little shove to the side? What's it going to do? The ant's not going to like it. It's going to squash the ant. Right? I've done something. I've changed the state of this brick in such a way that it can do what physicists might call work. Now, the ant's not going to probably call that work. That's just terror for the ant, but it's murder, maybe. But you see the point. I've invested something in this brick that allows it to do something now that it couldn't do before. I've given it gravitational potential energy. Now, when this thing falls off the shelf and hits the desk and makes a big noise, what's happened to all that gravitational potential energy that I gave it previously? Converted into kinetic energy, right? Which could be useful. So you kind of start to get an idea here. Now, this could apply in lots of, not just squashing ants. We could be doing things like harnessing energy that we're storing for later usage or things like that, right? And there are all kinds of interesting new approaches as we look at kind of a new energy future in our country. We got to think of some new ways of doing things. I don't know if you're aware of this at all, but like one idea is, for example, I'm just thinking off the top of my head here, how do we use solar energy or wind energy? And here we got, you can't drive down the gorge without seeing thousands of these new windmills going up everywhere. Sounds like a great idea, and I think it probably is. Oregon eventually will also be, Eastern Oregon will be just a hub of solar energy too, because we got such consistent sun from the south, and it's maybe not in Pendleton so much, but in the surrounding area, there's very little cloud cover most of the year, so that's coming too. What's the problem with wind energy and solar energy, though? Anybody know? Okay, yeah, it comes at the wrong times sometimes, right? If wind energy, you essentially the way our grid is constructed right now, you sort of have to use it or lose it. It's very difficult to store the energy that you harness from the wind, and so if you don't need that demand when the wind is blowing, it's not as useful. That's different from, say, a power plant, coal-fired or natural gas-fired or even nuclear, that you can just turn on when you need it, right? You can turn it on and turn it off, and that's fine. With the wind and the sun, you're kind of just at the mercy of nature. So the goal is, can we find a way to store this stuff and use it later? Well, there's a couple of different approaches to that are gaining a lot of momentum in scientific communities. One of them is you can take a whole cave full of essentially salt, and you can heat the salt up, and then the salt stores the energy very efficiently, and then you can just harness that thermal energy to turn a power plant or to produce energy for a power plant that you can send out when you need it. That's one thing. This is another one that's kind of weird, but I think it's really cool. You could take certain kinds of caves are really, really well sealed. And I don't know the geology of the whole thing, but if you take these large underground, and they're talking about, for example, the evacuated essentially holes where petroleum was pumped out in the south they're looking at. And I think in our area, I'm not sure, I think it's just naturally occurring caverns, but you can take these things and you can pump them full of air. And then certain types of gas will work better than others, but you can pump them full of gas, and what do you suppose you do then when you need the energy? You let it out. Yeah, you let the gas out, and so you've got all this pressurized air. You let this stuff out, it turns a turbine, and you create electricity. So do you see how that relates to what we're doing here? What's it take what are you doing to push that air into the rock? Well, it doesn't want to go in there. You have to do a lot of work to get it in there. You have to physically apply a force to push that air into the cavern. It stores, you're doing work on the gas. The work is storing that energy in the form of pressure. And then you can release it when you need it and disperse the energy on demand, right? And so just, I could go off on a million physics tangents, trust me, I'd love to, but we better get going on this. You get an idea, though, that this is a big deal, because if you want to calculate something other than our idealized situation where I'm picking something up at zero velocity, what if you don't pick it up at zero velocity? What if instead you do that, where I'm applying a force at the beginning and then it tails off and the thing decelerates at the top? That's not a constant velocity, and all the physics you're learning becomes completely invalidated then. You can't calculate that work because the only equation you know right now is this one, right? What's work equals force times displacement, right? But think what those mean. This has been pretty idealized. The force you're talking about is force all in the direction of the work, and the displacement is all in the direction of the movement. And we're assuming that this is sort of implied, and I don't know how specific you've been about this, but the implication has always been that it's moving at constant speed, because all the physics you're doing, because it's not calculus based, it's a little wimpy right now. It's going to get stronger when you get to college. It's all based on the premise that acceleration is constant, or zero, right, which is constant. And so, this gets a lot stronger when the forces we're dealing with, if this is a force curve, can be, actually nonlinear forces, like every force in nature, right? Then you can start to add up these same quantities that you're talking about in this idealized physics, using real natural force curves, right? If you do something like you hit a baseball, what's it look like when you hit a baseball? I had some really good equipment in McMinnville. And we had force plates and all these. We were able to do some of this stuff. It's really interesting. If you look at a force versus, we'll just call this a force versus time graph for that. We'll turn that into displacement later. If you hit a baseball, it looks like this, kind of goes up and it wiggles around a little bit, and it looks sort of like that. And so the force is highly nonlinear. I mean, it hits some spike in the middle, but you're dealing with forces that vary massively over short periods of time. So obviously, if you're going to do any physics with that, you got to use calculus. Right? All right. So how are we going to do this? This is the question. How are we going to come up with a way of adding up a finite area under some curve that's constantly changing? Right? What do you I mean? What are we going to do now? Let's think about this in terms of a strategy that is very similar to what we did before. When we wanted to add up, we wanted to find the slope of a curve at a point, slope of a tangent to a curve. What did we do? Well, we looked at slopes over intervals and just shrunk those intervals, okay, using a limit process. But we started off with something that was macroscopic and made it microscopic. Any ideas here how we can do this? And I know you're not going to have any ideas. What do you think? Do you have any ideas that?
Well, you got to start thinking. You just start from A to B, and slowly make multiple columns in the middle.
Ah, interesting. Interesting. So something like. Okay. Okay. What? So something like this. What if we? You're suggesting like that?
Yeah.
Okay, what am I going to do with those slices? I'm going to call them slices because that's a word I'm actually going to use quite a bit. What if I slice up the area like that? What am I going to do? Say that again. Say it a little louder. Ah, okay. So now I think. Tell me. So what you're suggesting then is I make these kind of maybe even widths. Okay, so they're easier to calculate. And by making them even, what are you saying about this top curvy part? Or are you suggesting anything
We
about
get a
that?
better idea of what each chunk is going to have for area.
Okay. But it's still going to be hard to add up these individual areas right now because, like, let's take this last one, for example. It's kind of curvy. Whoops. Wrong tool up here because it's kind of curvy at the top still. It looks less curvy, but it's still a little bit curvy. Okay, make them smaller. Good. Now, what shape am I gonna? So I'm adding up these areas. Then, what shapes are they gonna be?
Rectangles.
Okay, I could do rectangles. If I do a rectangle, that's one possibility. Let's draw a rectangle here. So a rectangle would look like maybe. Where do I stop? Like right there?
Yeah.
Okay. Okay, and then I get, and those are rectangles, right? And rectangles would be really easy to add up areas. There's the advantage for that one. Good. What's another shape I could use? Let's pick the next one and pick like a different shape. By triangle, do you mean have a slanted top on it? Well, I mean, I could probably, but a circle might be tough because fitting the circles in here is going to be. Oh, on the top, you mean?
Yeah.
Okay. Yeah. Now I could. That's a good idea. But the disadvantage, I'm going to tell, and there's a practical disadvantage here, is when I start to create shapes that are too hard to deal with, even though I've made easier shapes than what I started with, the formulas get to be pretty difficult. So we'd like to kind of walk a... Exactly. And this is a real practical issue because when our calculator does stuff like this, and I'm going to show you what our calculator can do, you're going to be amazed. This is... there's a whole new world on these calculators you haven't explored yet that you get to kind of look at now. You didn't know about this stuff, but... Okay, so let's say we want to do, I'm just going to make up some function here. Whoops. We'll just do x squared, and I'm just going to make my window go from like, how about if it just goes from 0 up to 2. Sure. I'll go from 0 to 2, and I'll just hit zoom fit, so it'll just kind of give us something like that. Now, what if I want to add up the area from 0.5 to 1.5? Okay, watch what our calculator can do. I can go second calc, and I can go down to number 7, and I can put in a lower limit of 0.5 and an upper limit of 1.5, and look at that. How about that? Amazing, huh? Let me scoot the bottom of the window up so you can see that a little better, so the wording isn't blocking it out. I'm going to make y minimum like -1. Oops. Do that again. Second calc 7 0.5 and check that out. It tells you the area. Now it tells you, this looks a little funny, but I'm kind of giving away the big secret here. That's sort of our calculus way of saying area. Okay. Notice this little integral sign. And it tells us it's 1.083333. So that's some 1 in, oh my gosh, I can't know what that is. That'd be not really that important. 1 in 1/15 through 30th or something like that. So anyway, something like that. But it gives us an answer. Adds up the area under the curve. And that is, by the way, an exact answer. If we take that repeating fraction and turn it into a decimal, I mean a repeating decimal and turn it into a fraction, that's an exact answer. Okay, so it did that pretty quickly too, right? How does it do that? Calculator's smart. How does it do that? Well, this is why, and this is really interesting to me. This discussion we're having is topical because this is the same kind of thing that programmers and mathematicians have to deal with when they want to write a routine for doing something like this. But they've got to weigh two things. They've got to make the routine simple enough that it can execute quickly many times, but they have to make it strong enough that it's going to be accurate. And the more accurate the approximation is, the fewer times it has to do this approximation to get the right answer. Does that make sense? Okay? It's kind of like if you want to get up the top of a mountain, am I going to take a bunch of really small steps, or am I going to take great, big, huge steps? Well, you probably don't want to do either to the extreme. You want to find the happy medium if you want to get up as quickly as possible. And so this is the discussion we're having right now in class, and you'll see this connection soon, if you don't already. How do we deal with this? Rectangles are a great choice because they're so easy to calculate, right? What was the other one? Do we have an idea what the other one we might consider? Well, okay, by triangles, I think I'm gonna. Are you sure you mean triangles, or do you mean the top would be a triangle? So you mean something like, so the whole shape would look like that, right? What's that? I'll give you a hint. It's got two parallel sides. The trapezoid. It's a trapezoid, yeah. Okay. That's a trapezoid, yeah. And there's one other possibility I'll throw out there, and this is kind of a weird one. What if you did something like this? What if you did something where you had, say, you did like a trapezoid, except the very top part, to make it a little curvy, we could make it a quadratic approximation. So for the top, we could take these 2 points and a point in the middle of the, if we went up here, and we could turn it into a quadratic approximation. And the reason I throw that out is because what we're going to find is this trick that I'm showing you, as awesome as it is, there are certain functions in calculus. I'll just tell you in advance, full disclosure here. There are certain functions in calculus that the math gods, with their sense of humor, have created to defy all our best intentions, and it won't work for everything. There are going to be some functions which are not amenable to our trick. And for those, we're not going to be able to get an exact answer. We are literally going to have to go back and make some approximations by carving it up into a finite number of intervals. And we're going to have to make a decision. Do we want to use trapezoids, or do we want to use what's called Simpson's rule and make the top curvy? And we're going to stick with trapezoids this year, but in the future you'll look at some higher power ones. Okay, but let's not focus on the those oddballs. Let's focus on the most of the functions that we can get exact solutions for, exact areas for. And so you kind of see the stuff we're going to do, right? And we'll just debate between the rectangles and the trapezoids, how about? Because those are both pretty easy to calculate, okay? And I don't expect an answer yet, but soon I'm going to expect you to come up with a definite answer as to which one we're going to prefer, and there will be one. There will be a definite preference once we start getting into the math. All right, so what about the math? Now, this is where this comes from, and we're not going to have time to launch into a whole bunch of calculus, but it's kind of fun to do this introductory stuff too. Where this originally came from, this idea was something that I can't remember who was doing this. I think it must have been Newton, but I can't guarantee that. Trying to find the area of a circle. All the geometrists, all these original mathematicians, these Greeks and Romans that were doing all this math, they got very, very good at geometry. You know, Euclid and all the Euclidean geometry you study in school that's really old stuff, really, really old stuff. We could add up, for example, we could take just about any polygon. Relatively early in this whole process, we could take any polygon, not even having to be a regular polygon. I think I have to probably, well, no, I don't. I can draw irregular ones too. I could take any polygon, and how could I slice and dice this thing? Does anybody know in a way that made it relatively easy to calculate the areas of any polygon? I could break it into triangles, sure. I could cut this thing up into, if I just start at one vertex, and I just connect to all the non-consecutive vertices, I can always break these things into triangles, and triangles aren't horrible to deal with, right? We can find areas of triangles. Very early on, people established formulas for calculating areas of triangles, and so I could handle polygons that way. So then what do you suppose we're going to do if we want to get a circle? That's a little tougher, right? A circle is admittedly, oops. Yeah. If I want to find the area of a circle, that was a problem. That was a problem. People for a long, long time were unable to even do very good approximations of a circle. Two cross sections, meaning straight across this way, sure. Cut it up vertically. We could do that. And the idea maybe you cut it into pie shapes and then approximate those pie shapes of triangles. Yeah, that's not a bad idea. And that's probably something people did. You still have that curvy part out there, but that's one way to approach it. Kind of say it again.
You can cut it out, take a straight line.
Yeah, well, cut it out. Well, you can find the perimeter. I mean, people could sort of find the perimeter by measuring it, but the area is tough. How are you going to find the area? Here's sort of what people ended up doing. They took the circle, and you got pictures. It was in color. It's out of your book, but when I took a picture with my camera, it didn't translate to color. I thought it might, but it didn't. Look what they did. They took the circle and they blew up a regular polygon to make the area easier to calculate. Right? They blew up a regular polygon from the inside until it pushed out against the circle, and then they deflated a big polygon from the outside until it pushed up against the circle. And those radii were, I mean, that was easy to do because now look what happens. You can kind of, we're not going to go through this whole process, but you can kind of get a sense. Yeah, you can kind of get a sense here, can't you, for how this wouldn't be that big a deal? Because, like, look, for example, then the radius corresponds to, see, there's the radius, right? And look at this little triangle that we've drawn here on the inside. The radius is related to that triangle, right? It's one of the side lengths of that triangle. Okay, that's good. That makes that easy to deal with. And by the way, we call this
And then the height of the other one.
exactly, yeah, look at that. And this red polygon that I'm drawing that's on the inside, this is an important calculus word. That's what we call the circumscribed, or excuse me, the inscribed. Whoops, got it backwards. That's the inscribed polygon. And then the one on the outside, which I'm going to probably run out of time, there's the radius, right? The one on the outside, etc., is the circumscribed polygon. And then wouldn't you agree that as I make the number of the polygon have more sides, the area between the two starts to get extinguished? This was literally called the method of exhaustion, which I think has a great double meaning because it would have been exhausting to do, but also it's exhausting the area from in between. And so as these two areas get closer and closer, you get a better approximation of what that area, that circle had to be. Pretty clever, right? So that's a great place to stop. Hold it there and we'll continue later.